Good. So thank you very much. Good morning. Thank you for being here. This is not going to be much about loops. There is only going to be a single little slide to connect to loop quantum gravity. I'm going to talk about what I think about the ontology of quantum gravity in general as a problem and what it forces us to do. Roughly, the way I think about the question of the metaphysics of quantum gravity, the ontology of quantum gravity, is that we have to reconceptualize the way we think about what is it to describe nature because of the quantum property of space-time, and the effort to come out with a new conceptual scheme. It's much more than just writing some equations, coming up with some numbers and compare with some measurement. So it's all the rest which is absolutely needed for making sense of nature, for doing science, for coming up with ideas and so on. I see quantum gravity as an open problem, of course, but there have been a lot of development in various directions. There are tentative theories of quantum gravity out there, more than one. They may be right, they may be wrong, we don't know, and I think that's where the situation is. The scientific problem, the way I understand it, the different ways to think about quantum gravity, the way I understand it is the following. There are phenomena in the universe for which we know that without quantum gravity we don't have the theoretical tools for describing them. I mean, there are phenomena we don't understand, but we think it's not because we're not smart enough yet. Sort of, it might be reasonable to think that most of the things in the universe could in principle be accounted by classical generativity and standard model with quantum field theory. But then there is also phenomena, and in particular, we see the black holes in the sky, we see matter falling in. I mean, what happened to matter after it crosses the horizon? Well, it falls in for a while, and then we don't know, because it gets to the R equals 0 singularity. We don't know what happened there. The Big Bang, we have a good history of the universe, surprisingly effective up to some point, and then we're in the dark because we don't have quantum theory of gravity. Or more precisely, because our equations don't work, and we think we know they don't work because we expect gravity to have quantum properties, and we don't know how to describe them. So I see quantum gravity as a very concrete physical problem. How to find the tools for describing those phenomena in the universe where the gravitational field cannot be described in the classical approximation. Now, it's notoriously complicated, but I think it's complicated because quantum mechanics is complicated, because gravity is complicated. And I think a lot of the confusion around the conceptual difficulties of quantum gravity have to do just with the conceptual difficulty of quantum mechanics. We're all aware a lot, and there's no consensus of how to think quantum mechanics in a single clear way that everybody agree. And then also we have different ways of thinking quantum mechanics, which are all good and liked by somebody and badly disliked by everybody else. A gravity situation is it's a bit better in the sense that there is consensus, but it's tricky how to think about gravity. There have been decades of confusions historically. The people who work with relativistic gravity have no doubt of how to use it cleanly. But when you come into the theory from the outside, it's very confusing. I mean, Einstein was totally confused for long. You know, he wrote papers in which he says gravitational waves are a gauge, they're not really physical. And then he changed his mind. He wrote papers about the universe stops at R equal to m in a Schwarzschild solution, so on. So gravity is tricky. So most of what I'm going to say is how to think about quantum. Just go back to the question about how to think about gravity, and then quantum gravity from a given way of thinking about quantum, from a given way of thinking about gravity, comes together. I will just have a slide or two, a bit of formalism. That will be the only little technical thing, not about loop quantum gravity, to make clear what I said before in a more technical way, to see how to address it. And then loop quantum gravity is just 3 lines to see how this is implemented in loop quantum gravity. All right, so let me start from quantum. Now, let me start from, even if I don't buy the idea, the traditional thing that you have formalism, you interpret it, okay? So the formalism of a quantum theory, any quantum theory, can be given in a variety of ways. Path integrals, algebraic, quantum mechanics, but they are centrally overlap largely. Let me just pick one, the most common. You have a Hilbert space. You have an algebra of observables, Hilbert space of square integral functions of R, algebra of x and p, which is d over d, I h bar d over dx, and you have an Hamiltonian or something that gives the dynamics, gives the evolution. Now, what I want to stress, and that's the main first point, is that whatever way you think about the ontology of the thing, it is in the algebra of observables and not in the states. Okay? Including your, if you're an Everettian, if you're a many-world guy, like David Wallace, except if you are Sean Carroll, mad dog Everettianism, in which you want to believe that you can do without this. Okay? But I don't believe it works, and it's just him. Okay? So apart from this extremists, they're always extremists. I'm an extremist in something else. When we talk about what are we describing by a quantum theory, we always talk about the algebra of observables. Including, I said in many words, because in many words you do think that you have this overall wave function of the universe to which you attribute a heavy ontological weight. I don't like it, but if you like that. But then when you describe something, you need the split, maybe it's the next page, you need the branching, and you need that in a branching there is a state which is a form sum over n coefficients, eigenvalues of some operator of one system, eigenvalues of another operator in another system, and the eigenvalues are the thing we see. The color of this, so the object we see, how we describe the world, is in terms of the eigenvalue of the system. So in terms of what is the algebra? For instance, for a particle is a thing which has a position and has a momentum. A qubit is a thing which is up or down in various possible directions. Electromagnetic field is a thing, yes?
Is it matter with Heisenberg-Schrödinger picture? Or
is nothing to do with Heisenberg-Schrödinger picture so far. That will have to do with time, come later. Not at all. It's a matter of where do you want to read the ontology, in the states or in the variables. Okay, if I only give you the states, you're blind. It's like Hegel night where all the cows are dark. It is no ontology. The ontology is in this, the set of variables is to those variables that we attribute. If you're an operationalist, it's to those variables that you think you have a machine that tells a number. So each element of the algebra is a machine that gives you a number if you're an operationalist. If you are not an operationalist, it's the actual thing that we're talking about. Okay? So the ontology is determined by the. Here is just I just put the relation between the algebra and the Hilbert space, between the observables, the operators, and the states. I don't like to call it observables because it's too heavily. These are the variables that we use to describe the world. It's sort of double. You can view a state as a function on the space of the variable. So a state is something that associates to any observable a number, which is its mean value. That's one way in which you connect. Also, each observable has a spectrum, which is a subset of the real number, which, by the way, is defined independently of the Hilbert space, just algebraically. There's an algebraic definition of the spectrum. It's a set of A for which this A minus A, the identity, have no inverse. And, you satisfy the eigenvalue equation as an equation on state here. So, because this form an algebra mathematically, automatically each observable comes with a spectrum, which might be discrete. Okay, like here, qubit, the angular momentum in one direction is just two values, it's not continuous like in the classical in the classical limit. I'll come back to that in a moment. But maybe I want to say the physical thing we see is not the mean value, is eigenvalues. Yes?
Can I just a clarification?
Yeah. Oh no, that's exactly the point I'm stressing. It's not.
You're going to choose some particular
Absolutely.
subalgebra of that.
I'm not going to choose. The theory is defined by a certain particular subalgebra. Otherwise, we would have only one quantum
Okay,
theory.
yeah, so part of the physics is to determine
Exactly.
what the physical subalgebra
Exactly.
algebra
Exactly.
involves.
The decision theory is a choice of a particular subalgebra. Yes. And I stress it. This is also true. I had a long conversation with David Wallace a month ago. That's also true in his way of thinking many worlds. So this is also part of the rectangular world. Yes?
Right. Could you finish the examples at the bottom of the page before you were interrupted? What's an electromagnetic field in one sentence?
What is the electromagnetic field?
I mean, you were giving like a snappy formulation of a particle is blah, blah, blah.
The electric field.
Yeah. What is that in one sentence? What is that?
What is the electric field?
Yeah.
I can go to a hardware store and buy a machine which measures the electric field in one direction. It's an oriented machine, so in that direction, give me a number. 25, forgot the unit. If a magnetic field, a Gauss.
Yeah.
25 Gauss in that direction. So it's an observable of the thing. Now, of course, that's easy so far. Of course, I'm putting all the thing on the carpet. Now let's take out of the carpet the things. If you measure if something has a position, if a quantum particle has a position, it doesn't have momentum at the same time in the usual sense. So these numbers which associate to the variable x and p come about when your particle a la Bohr is interacting with an apparatus that measure x, or when interacting with an apparatus to measure p. In many world interpretation, when it happens that there is a branching such that x is diagonal branching or p is diagonal branching, in that case you have an x, and in the other case you have a p, and in some cases you have neither. Okay? So therefore, these variables that take value don't refer to the system itself, refer always to the system and another system. And the difference between the way this is played in a sort of Bohr textbook, quantum mechanics, and in relational quantum mechanics, which is a version I prefer, is that in Bohr perspective, this is the classical world, this is the classical apparatus. In relational quantum mechanics, this is an arbitrary system, this is an arbitrary system. When there is an interaction between the two, there is a quantity which is a quantity of one system which is involved in interaction, and this quantity has a value. Again, many worlds is when this particular, here is what I was looking for, when this branching in this form. I'm not going to go into do you need the coherence for saying that the value of the variable is realized or not. I mean, this is irrelevant for that. So therefore, the value of the variables is not defined outside interactions. And by the way, this is also true for a subtle way for a much subtle way in the Bohmian interpretation, Barry, because well, I've written a paper about that. In the Bohmian interpretation, to make sense of what happened in a interaction, you do need the coherence for a subtle. Well, I'm not going to forget the Bohmian interpretation. Yeah. So they're not defined outside interaction. This means that every time we talk about the ontology of quantum mechanics, that's where I wanted to get at, we are always thinking in terms of a Heisenberg cat. There is a variable of a system that has a value with respect to something else, with respect to Bohr apparatus, with respect to the branching, with respect to relational quantum mechanics system. Okay? This is a key, which means that you are always, in quantum mechanics, describe a system with respect to something else. You can hide very much this, but it's always there.
Sorry, Carl. Just another clarification. Is the value an eigenvalue of the operator that corresponds to that variable, one and only one eigenvalue?
Yes.
It's one of the eigenvalues.
If you are a relational quantum mechanist like me, definitely yes. If you are a many-world guy, you think that there's another world in which, another branch in which the other is realized.
The other branch.
Yes.
Okay.
Yes. So that's what I'm saying. It's heavily dependent. The way you think about the ontology is heavily dependent on the interpretation of quantum mechanics. A lot of people like many worlds, and they're fine. They're my friends. But they, and I think it's a good way of thinking at sometimes what happens. But I think in terms of ontology, I prefer to forget the other world. I prefer an ontology only branch in which one branch. Okay. But whatever you do, you always have an Heisenberg cut. That's essential. And also, I want to come back to the fact that the variables that we observe, in general, are always part of the spectrum. So in general, they may very well be discrete. Now, this is about the variables. What about the dynamics? The dynamics in quantum mechanics, careful. It's misleading, in my opinion, saying, oh, we have the Schrödinger equation. Because the Schrödinger equation is about probabilities of something, evolution of amplitude of something. What we have is probabilities associated to one realization of eigenvalue and another one. So one eigenstate and another one. So we have transition amplitude. What quantum mechanics tell us, if there's an Heisenberg cut, okay, you see the eigenvalue A, what's the probability after time t to see the eigenvalue B, maybe of another observable, and there are formulas for that. So the quantum ontology, it's something like that. With a system, and there is a variable realized with respect to another system, and then there is a dynamics, and there's a process, and there is a value of this realized to another system. So what we're talking about in quantum mechanics is not really things, it's processes in which one goes from an interaction to another interaction, so to say. So there are processes, there are variables. These variables have to interpret them relationally. So it's not that the particle is at x. The particle is at x with respect to the screen. And if you think about the Wigner friend, nightmare, the particle is at x with respect to Wigner friend, doesn't say anything with respect to Wigner. Okay? So there's deeply relational strand going inside quantum mechanics, which is a way of expressing the contextuality of quantum mechanics, which is the thing that confuses us. There's discreteness and always zero. That's all I wanted to say about quantum mechanics. Let me go to gravity. So forget quantum mechanics entirely. The world is classical again. Well, let's play the same game. We have a formalism, and we want to interpret it. Now, the formalism, general relativity, is that there is a gravitational field. There are maybe other fields, set of other fields, electromagnetic fields, Higgs field. There are particles, if you want, maybe in some approximation. There are particles that have an action for all that. Now, what is the ontology of gravity? Well, in a sense, it's easy. That's the thing described by Jim New. That's the thing we're talking about. And Jim New, from this perspective, it's a variable in a dynamical system. So it's like a pendulum, it's like a particle, it's like the electromagnetic field. Okay, it's one of the things that have equation of motion, that have variables, that have a Lagrange, and so on and so forth. So from this perspective, the gravitational field is very much like something else. Okay, and in particular, being a field is very much like the electromagnetic field. It's the same sort of things as the electromagnetic field. Okay, I've been insisting a lot in my writing on that. However, as Sam Fletcher likes to remind us, yeah, we're all similar, but we're all very different, right? And in particular, the gravitational field is definitely very different than all the other fields in a number of quite crucial ways, substantial ways, which one can list. Okay, it's coupled universally, blah, 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 a number of things. But there's one which is stronger than all the others, I would say, that makes it so special, which is that this field admits a reading in terms of what we call the geometry of space and chronogeometry of space-time. I don't know how to call it. So when we talk about the angle between two lines at a point, and we measure this angle, what we're doing in general relativity is we're measuring the value of the gravitational field in this point, and the angle is defined, the cosine of the angle is just this quantity here where this is normalized, this is normalized. When we talk about the length, the surface, the volume of something, we always measure the gravitational field. And of course, when we say that, I've been talking for what, for 10 minutes, I forget, when we're giving a statement about how much time is passing, we're talking about the measurement of the gravitational field along a line, right? It's the same formula here for a time like, with a minus, this is time like geodesic. In fact, as some remind us, so much so, if I read you right, that you can even reduce all possible variables, all possible measures that you can do on G mu, just the time measurement, okay? So you can think just of describing geometry. I would say geometry is not an a priori like in Kant. Geometry, it's at the light of general relativity, we have realized that it's nothing else than a set of special features of this field, which is a very particular field because it can be interpreted in terms of geometry, chronogeometry, and so on and so forth. That's the easy part. Now, where is the hard part? The hard part, as everybody knows, what has created confusion for Einstein, for everybody, forever, is that the Einstein equation invariant are the general coordinate transformations, which Einstein himself at some point wrote a paper saying they shouldn't be invariant under general coordinate transformation because we would be completely confused about space-time if they were. And then 1 year later, he wrote a paper with the Einstein equations, and in fact, we got completely confused about space-time, exactly like he predicted. Okay? But we can come out from this confusion. There's an L here missing, general coordinate invariance. And there are, that's important. There are three, so there's a huge discussion in the literature about how to think about the variables in a up to diffeomorphism, invariant context. And there are three ways of thinking about that. And people keep insulting one another because each one is focused on one, and they're all correct. Okay? They're all correct, but they're different, and I think one gets some clarity by separating the three. First one, I have colleagues, Alejandro Perez, that would say this is the only thing you can do, everything else is wrong. Is to say physical quantities. I mean, you take the theory here, and you say the only thing that you have to connect to observation is quantities which are independent from the coordinates. So forget about the coordinates. The coordinates are just in your little calculation, and then it has to be independent of the coordinates. For instance, LIGO, black hole gravitational waves, you do a long calculation, you come out with the fact that the picture that comes from your LIGO machine is this one. This picture is independent of the coordinate, and no coordinate there, it's a picture. This is the whoop of the detection of the gravitational waves and the collapse of two black holes. That's a prediction of GR, okay? It's perfectly correct. But you can do also something else. You can say, oh good, I have some fields here. Let me choose some of the fields. One component of G mu nu, for instance, or more conveniently, some matter fields, some matter or some particles, and just attach the coordinate to that particular thing. So gauge fix the coordinate to that. There's nothing wrong with that. It's just a gauge choice, describing the choice. Now the coordinates are not free. You break completely the indeterminism of the Einstein equations. You have to add some equations to the Einstein equation, to the equation of motion of your matter, which says that the coordinates are attached. So you attach the coordinate to object in the systems, which don't need to be matter necessarily, but it's very convenient to have matter, because to do that within gravity is complicated. That's, for instance, how people do cosmology, right? In cosmology, you exploit the fact that galaxies don't cross each other too much. You assume that they never cross, which is wrong, because the Milky Way and Andromeda, as you know, they are going to collapse. And you say, let me attach the coordinates to the galaxies. So the coordinate is the name of the galaxy. and that fixes a space coordinate, and then say, let's imagine that in each galaxy there is a clock. I mean, forget that there's different potential inside the galaxy, just assume everything is more homogeneous than what it really is, and you choose the t to be the clock, the proper time along the galaxy. That's perfectly okay. So now coordinate physical is meaningful, and you can forget gauge invariance. The only problem is that your equations are not Einstein equations and the equation of motion of matter anymore. They also have all this extra gauge fixing conditions, which may complicate or simplify the matter depending on what you're saying. But there is a third possibility, which is the one which is mostly confusing, which is to play the same game, but not with one of the ingredients of the variables in your reference system, but with some variable, something which is outside your reference system. And that's what we do a lot in the following sense. Imagine that there is all the quantities described by the reference system, but there is something else in the universe. For instance, there's you with a spaceship going around with rods and clocks. Okay? Imagine that you disregard the equations of you moving with rod and clocks, and imagine that you disregard the T mu nu of your spaceship and your rods and clock. You can do that. Why not? Nobody forbids us. Then you attach your coordinates to your own rods and clocks. You can do that. Why not? Okay. Now you have exactly the Einstein equations for the previous system. They are underdeterminate, but you understand why they are determinate, because you are forgetting how you're moving in space-time. So you have thrown away your own. And now the G mu nu is directly measurable. Okay? So if I say, I choose my coordinate system here so that this is the x direction, this is x equals 0, and this is x equals 1, then G xx, and I assume that G mu nu is sufficiently constant here, then G xx here, it's exactly the square root of 20, 40, 60 centimeters. Okay, it's observable. So G mu nu is observable in this sense. Okay, and notice this is very clear here, but it's also implicit here because of that's how you extract coordinate invariant quantities. There is a deep relationalism also here. Every time we talk about localized variables, they are never localized with respect to coordinates, with respect to something given a priori. They are localized either to objects within the theory or to objects that are outside the theory, but we assume they're there. So much so that the indeterminate is interpreted as forgetting their own equation of motion. Oh. Okay, so how do we go to quantum gravity? We just put the two things together with one key idea, and that, I think, is the key idea that can make this work. The ontology is just a gravitational field. The variables, I can think in terms of geometrical variables. They're relative in a double sense. They're relative quantum mechanically with respect to the other system I'm observing to. And since I will some sort of locality, they're relative in the sense of location with respect to something I locate them. And so here's the key idea. Identify the Heisenberg cat with relative localization in general relativity. So in other words, I have space-time. In space-time, I have a quantum process somewhere, the matter that falls in the center of the black hole. Okay? I decide to put my Heisenberg cat around in space-time the region where I cannot disregard the quantum mechanics of gravity. And then I describe the process, the quantum physics of the system as it looks in reference to whatever is outside. So now, a space-time region is a process which takes me from the interaction between the system and what is outside before to the interaction in the system and what is outside after. So a region of space-time is a quantum process. it's what gives me the probability amplitude of what I can say in Copenhagen language, what I can measure here given what I've measured here. And that's exactly how we're using quantum gravity now to try to apply it to some.
What does this say at the bottom?
Here?
Yes.
Oh, it's just a badly cut transparency.
Oh, okay.
Now, how much time do I have? 0 or?
It was the key.
Yeah, it's. Okay. One slide and a half, slightly more technical, to see how this can be implemented concretely. I think this is sort of elementary theoretical physics that should be well known, in my opinion, which is the Hamilton function and its quantum analog. Take any dynamical system with a configuration space C with a variable which can have many dimension Q in C, and what we want to describe how it evolves with time. Okay? So there are equations of motion, they come from a Lagrangian, there is an action. Now there is a quantity which is the Hamilton function, which is not the action, careful. The action is a function of the trajectory. For every line here, you have a number. The Hamilton function is not a function, it's a function of q, t, q prime, and t prime. So the initial and final position in time. And is defined to be as the value of the action for the unique trajectory, if it is unique. If it is not unique, it's more complicated. I'm not going to give you the full story. For a simple system, this is unique. That starts at time t at q and at time t prime at q prime. Now the Hamilton function is fantastic, and when Hamilton found it, he lost his British aplomb and wrote, I found most beautiful thing. Lagrange function defined the dynamical theorem. Mr. Hamilton himself, function solves it. It has these properties. If you know this function, you know everything. You take a derivative with respect to q, you get the momentum, you put it equal number, you invert, you have the general solution of the equation of motion. Bingo. So it's all written there. More importantly, it treats q and t on the same ground. And that's going to be crucial for the problem of time in quantum gravity. It's just exactly the right thing to do. So you can call qt, you can call the space here extended configuration space. Okay, and this is a function of 2 points in extended configuration space, and you don't have to say which one is time, which one is the dependent variable. You just talk about. I use the language that T is a partial observable, Q is a partial observable. TQ is the thing we're interested in, the event in quantum mechanics. Why it's useful for the problem of time? Because if you parameterize the system, for all of you who know about the story, and you describe the same system as Q evolving in some parameter tau and T evolving in some parameter tau, and you compute the Hamilton function, tau drops out. And in general relativity, the coordinates are exactly like this tau here. So the Hamilton function of general relativity drops out the coordinate. It does automatically for you the work of solving different Morse invariants. Now, why it's so interesting? Because this, let's look at this quantity in quantum mechanics, okay? Eigenvalue of q, eigenvalue of q prime, transition amplitude in a time t minus t prime, okay? This looks to treat q and t very differently, but if you go to the Heisenberg picture, which is somebody was asking before, namely you define the Heisenberg operator, and you define the Heisenberg eigenstate as the eigenstate of the Heisenberg operator, then you see it looks like it's treating q and t in the same manner. And in fact, this is what, if you are Feynman would say, this in Feynman-Gibbs at the beginning, he says this is the way of thinking about quantum mechanics. That's the correct way of thinking about quantum mechanics. Functional integral starting from qt or arriving qt prime, this is what tells you what the probability of the amplitude of going from here to here. Now, what is the relation with this thing, which is everything you need to know about quantum dynamics, and the Hamilton function, which is everything you know about the classical? It's fantastic, it's just that. This, to first order in h bar, is just the exponential of the Hamilton function. Okay, so this is clearly the clean way of viewing a dynamical system. Okay, this satisfies the Schrödinger equation in both variables. This satisfies the Hamilton-Jacobi equation, and the Hamilton-Jacobi equation is the Eichner approximation of the Schrödinger equation. In fact, this is how Schrödinger got to quantum mechanics, right? To reinterpreting the Hamilton-Jacobi equation as the Heisenberg, as the Eichner approximation. So, in gravity, here it is. There is a Hamilton function associated to a region of space-time, which is if you give the gravitational field and the other field here, and the gravitational field and the other field here, you have a function of the field here and the field here, out of which is the value of the action computed on the solution of the equation of motion that interpolates, which gives you the Einstein is equivalent, knowing that function is equivalent to knowing the Einstein equation. And in quantum mechanics, if you compute the functional integral inside here, in principle you have everything. If you can make sense of this equation here, you have everything. But what is this equation? Is the transition, is the thing that gives you the transition amplitude between measuring something here and measuring something there. Careful. Remember how this was defined in the previous slide. X and x prime are not classical variable, are the eigenvalues of some set of operators. Right? That's how the thing was defined. These are labels of eigenvalues. So if you can make sense of that in a well-defined theory, you don't expect here to have the continuous field. You expect to have here a sufficient set of eigenvalues of the operators that describe the spectrum, element of the spectrum of the operator that describe the thing, the gravitational field and the other fields. So I can close finally and say how is realized in loop quantum gravity. That's just a penultimate slide. Without going into loop quantum gravity explicitly, I'm just telling you. So we have variables, and variables are what describe what happens here. So on a three-dimensional slide, right? This is a four-dimensional picture. This is three-dimensional. This is three-dimensional. At some initial time, I measure something, or I interact with something, and so I need variables, and I need variables for matter, but in particular, I need variables for gravitational field. And it's very convenient to use geometrical variables because that's the easiest way in which we think about gravitational field. Okay. And since this is a space-like, one way of viewing this is imagining that, remember, there is a physical system outside. Okay? I'm not in the nothing. So I can imagine here that I have something which, with respect to the external, defines some regions, a certain number of regions, and I can measure, for instance, the area and the volume of this region. So this sort of bunch of sub-regions is a three-dimensional thing. And I measure the volume and the area of the surfaces. And then I have an eigenstate. And in loop quantum gravity, the operator corresponding to that are well defined in Hilbert space. Is a spectral problem solved, and we know the eigenvalues of these things. And the eigenvalues turn out to be discrete, both these of these. So we have a basis in the Hilbert space, which is given by, of course, I'm hiding a lot of details here, which is given by the structure of how it's connected to that, which is a graph. I have a point for each one of these. And on each dot, which represents the volume, I have the eigenvalue of the volume. On each line, which represents the surface, I have the eigenvalue of the area. So these are the states. And then the dynamics, what it is the transition amplitude between one of these states and another one of these states. The graph can be different, of course, and the eigenvalues can be different. And loop quantum gravity, took 20 years to figure out, but we have an explicit formula for these things, which maybe the one that good Lord used or not, we don't know. That has to be checked experimentally. But we have an explicit formula for that. To be honest, we don't have an explicit formula for that. We have an explicit formula for that in truncation. So we have a sequence of truncations and a hope, praying Madonna, that the truncation would in some sense converge we don't know. There's a lot of things which are open. This is defined order by order in some truncation. I don't consider this a problem because that's the same of how you do in QED and QCD. You define the theory truncated and then you expect it to converge. So that's my last slide. I just want to summarize. I think one can make sense of quantum gravity, quantum space-time, but with a lot of conceptual cost with respect to a simple classical world where you have things moving around in space-time. I mean, the world out there, you're outside. First of all, you have to describe things relationally. So you're never describing the world from outside in this respect. You're only describing the world from inside. You're somewhere and you describe how a system reacts with respect to you or how a system reacts with respect to another system. In that logic, a space-time region is not an a priori, it's one of the processes that you're describing. That's the key, I think, output in terms of the ontology of the thing. A space-time is not something which is before the process, is the process itself. It's not the process that happens in space-time. Space-time is the process of something happening. We describe processes with the formats that we have. So the ontologies of gravity in particular is process between space region, which are described by variables, which are the things that we can in particular measure using geometrical variables. I wish I could do that with purely chrono-temporal things. I think in principle why not, but that's not the way it's realized in quantum gravity. So the variables, we know what they are. They describe a gravitational field and probably other things. And in particular, because they describe gravitational field and because gravity can be interpreted geometrically, they can be geometrical variables. Crucially, discreteness comes out from the theory, right? From the spectral resolution of the operators. That gives a discrete picture of space-time, of course. So the kind of things that Theo and Sumati were talking about, and they were showing that there is a way of thinking of that which is not incompatible with Lorentz invariance. The theory is deeply conceptual, and there is this profoundly relational underpinning of all that. And the thing I like is that in quantum mechanical, the relationality is because variables are realized with respect to system with another system. In relativity, the relationality is about location. What I mean by location is not where something is, but where two things are with respect to one another. So there's no meaning in where something is. A function of x and t is not physical unless I say what x and t mean. And to do quantum gravity, I think the key is to connect the two. So to use the contiguity as the way of defining the Heisenberg cut between the quantum process that you describe, which is a piece of space-time, and the rest.
All right, now we have a comment from Emilia Margoni.
Sorry?
Okay, right. So thank you very much, Carlo. That was extremely inspiring. So I will just try to provide some comments to open the discussion. And I will try to stick to 3 comments for the moment, but maybe we'll keep on discussing during the Q&A. So as far as I can understand, conceptually, what we're trying to do is basically taking principles and somehow methodologies from quantum mechanics and from general relativity and try to bind them together in a way that makes sense. So the first aspect I would like to hear more about is, it looks as if from both the presentation as well as the paper I read that you wrote with Francesca, at a certain point you write that quantum mechanics is not a theory about the fundamental structure of reality, rather it is a theory that allows us to understand which may be the quantum behavior of systems, no matter whether they are elementary or they are composite. So it looks as if you're attaching a specific role to quantum mechanics. So I think this may be a good starting point also for the discussion that Faye was suggesting yesterday, whether you would take quantum mechanics as universally applying in this sense, whether you would take it as a sort of meta theory that should apply at all levels of physical reality. Then the things that I find most fascinating about relational quantum mechanics, as well as the application you provide in the context of quantum gravity, is the role of observables, observability. So as far as I can understand, 20th century physics has been concerned about trying to figure out which may be gauge invariance quantities. So in 1930, Dirac underlined the relationship between transformation and invariance, so much so that a system which is characterized by transformation and associated invariance somehow signals the presence of irrelevancies. And of course, as this is connected to symmetries, in the sense that symmetry describe transformations which leave a system invariant, it looks as if there is a connection between symmetry, equivalence classes, and the notion of observability and non-observability. So in Dirac's balance, the introduction of constrained Hamiltonian system was precisely that of trying to single out which may be these irrelevant parameters. So in his balance, gauge invariant quantities are what matter from a physical standpoint. And that's where we're discussing about the ontology. I guess this is something that should be stressed out. So depending on the way in which you interpret these gauge degrees of freedom, you may find redundancies in the physics or redundancy in the mathematics. So it looks as if in your interpretation and in the classification you provided with Francesca, you discuss about the fact that gauge degrees of freedom can be interpreted as unphysical, as in the case of Dirac's balance, at least in his 1950 work and 1964 paper, as constrained, or rather as relational. And it looks as if, I mean, these two aspects are strictly connected and pointing towards what do we mean by gauge degrees of freedom. So I was wondering whether you could expand on that and why we should favor the relational interpretation. Which leads us to the third aspect, which is what you call the boundary strategy in the context of loop quantum gravity. So you take somehow hints from these considerations, and as you said, you define a process as a space-time region in which I can define a sort of Heisenberg cut, and I can take observables to be living in this cut. So you claim that I do not need Dirac observables, but I can just use partial observables to account for the way in which transitions amplitudes are resolved. And again, I was wondering what's the relation with the understanding of gauge degrees of freedom, and which are the reasons for, again, taking that option. And so the boundary strategy is connected at least to two aspects. The first is the role of truncation, and generally speaking, the role of limits in order to perform it. And the other one, which is the thing I'm mostly interested in, is what notion of process is at stake there? Can we really speak about processes? Because as we discussed yesterday with Faye, it looks as if, of course, there are different blends of processualism, but it looks as if processes are connected to change and happening in a strong sense, namely as the coming into being of things, as the birth of some, I don't know, events or whatever. So I was wondering whether by embracing the relational strategy and talking about partial observables, whether the notion of process at stake is this one, or whether it's closer to the Lagrangian formalism, and so to the idea that, as you said, I can define this function from initial and final states, and so I can call this a process, but in the end, the states are already fixed. So yeah, this is what I'd like to hear more about.
So, Carlo, do you want to reply?
Maybe just a few words, because that's super good, but it's too much.
Yeah.
I mean, so this is a weak conference. You've underlined the plan for a weak conference. So let me just say one word for each line. The first point, I think you're completely right, and in my opinion, there's a widespread misunderstanding of quantum mechanics as the theory that describes what happened at some level. I don't think this is what quantum mechanics as we have it is. Quantum mechanics is discovering that all variables in all dynamical things actually observed sufficiently precise have a quantum behavior. So quantum mechanics applies to atom, to big pendulum, to galaxies, to everything. And if we view it this way, we get more clarity. So there's a universal property of nature at whatever scale we do. So it's not about elemental equals. So that's, I just totally agree that it's crucial for the rest. The second point, it's related to the third. The second point is that for me came from an observation, which is the following, that the notion, given a specific dynamical system of the ones we use to describe the world, with a clear distinction between what is gauge invariant and what is not gauge invariant, and when we use it, we can just treat the gauge variables as mathematical redundancy. But we don't describe the world with just a theory, we describe the world with a collection of related theories. And then what happened historically is that the same theory, which has this mathematical redundancy, when it becomes part of a larger theory, it's exactly those variables that interact with variables of another theory. So they weren't so physically relevant as they looked. In the context of larger theory, those same variables acquire meaning. And so this opened a discussion. Gauge is also related to, so I see gauge variables as the handles through which the system can couple to something else. And this is exactly what happened when I say that the G mu itself becomes observable. In a pure gravity theory, it's obviously not, because of but when I couple with something else, I couple exactly G mu with something else. So now with respect to something else, the individual component of G mu. And that's an interesting, very interesting story. The role of truncation is a big discussion by itself. You are right that I just hid under the carpet all the discussion. And what do I mean by process? So I'm not going to enter in that. And what I mean by process is I think, and that will be the point, that there is a sense of talking about physics as descriptor of happening or processes, even in a non-time oriented manner. That's the core. So I think that if we accept the idea that fundamental theory is not time oriented, not for that reason we have to say, oh, therefore there's a static universe where nothing happens. No, we're talking about happenings, but the notion of happening doesn't necessarily require that there is oriented order in which things happen. And this is also a big discussion, which is another chapter.
Thank you.
All right, so we have a bit of time for discussion. Okay, so just give me some time to look at everyone. Okay, we haven't heard Vincent a lot, so you are on.
So hello everybody, I'm sorry I just arrived this morning, so I was just late. So hi Carlo. I will have many questions very quickly. Could you elaborate a little bit on the ontological picture in the end of all this? Because you give hints. So what's exactly the ontological picture there? Think about now the quantum cosmological context now. And you're saying we cannot look from outside. So what's exactly the ontology there? And what's the connection with what we know from the usual quantum thing about probabilities and this kind of thing? This is one question. The other question is, to what extent is, you talk about space-time, quantum space-time and so on with quotes. To what extent is it still, are we legitimate to talk about space regions space-time or quantum space-time there? Are there regimes where there might not be a correspondence with space-time? So we could have quantum gravitational degrees of freedom in certain regimes where there might not be a clear correspondence with classical space-time as we know it. So yeah, these two questions, and maybe also the more generally the strategy of having these two kind of relationalism in quantum on the quantum side and on the correlational side. So, but these are two very different. So, what is the intuition there of saying that somehow they point towards the same fundamental feature of the world instantiated in quantum gravity, for instance?
Yeah. So I think Francesco, you want to talk about emergence.
I'm talking about all the three questions.
So let's move to the next question.
So,
Let me just say something briefly, but then Francesca, I think, will fill some details. So you're asking about the overall ontology, and you mentioned cosmology at some point, right? I don't think that cosmology changes anything here, and I'll say why. The idea here is that when we're doing science at the light of quantum mechanics, the conceptual structure of thinking, there's a world there, that was happening in the world, I described what happened in the world, is not good. Forget about that. The way to think about that is that we are in the world, okay? And so what we do is that, of course there is a world, the world is very real and out there, but to describe it in physical terms, what you have to do is to break it in pieces, okay? You always have to break it in pieces and describe how one part of the world affects the other, how it looks from the perspective of the other. And our theories are very good because there is a remarkable, whatever you cut it, they are such that it works. And the tensorial structure of quantum mechanics is exactly telling us that. The fact that you can move the Heisenberg cut freely outside the quantum system is exactly what allows you to do that. So I think this way of thinking quantum mechanics forces you to give up a sort of, the world is there and have a full description about it. It doesn't work because it's a description with respect to something. If you don't have this something, there's nothing happening, so to say, because things happen in image. So that's the first point. So in a sense, part of my answer to your question is you're asking something that might not have meaning at the light of this way of thinking. Okay? Concretely, it's very easy. So in quantum mechanics, you have a quantum phenomenon, you describe how it affects whatever is outside, which are the variables which are realized. And every time we actually use quantum mechanics in our real life, we do that. Okay? In a laboratory is very obvious, but the quantum mechanic applied to the sun is also very obvious because there's some process there. You isolate them, so that's the probability of this something to happen. This is also true in cosmology, because maybe Francesca is coming back to that, I don't know. Don't confuse cosmology in the sense of description of the scale factor or the large degrees of freedom with cosmology in the sense the theory of everything, the quantum theory of everything. The quantum theory of everything, throw it away. You still have the quantum theory of the scale factor. To be I can describe the electromagnetic field in this room, considering myself outside from it, even if I'm immersed. So that's not confuse dynamically independent from located inside. What was the second part of the question? I forgot. How does this plays out together? Oh, that was the third one.
Yeah, or maybe just on, it was about
how the probability comes about.
Yeah, but maybe related to what you just said is to what extent is your work and all this related to this particular view on quantum mechanics, or do you think we can make sense of your work in quantum gravity independently somehow on the way we understand quantum mechanics, or is it tied fundamentally to this view?
It's a very good question. I'm not sure. This is one thing I discussed a lot with David Wallace last month. I always think in terms of relational quantum mechanics, which is what comes natural from this perspective, because then you have variables that take value when there are two systems. But I think that if you take other ways of thinking of quantum mechanics, you should end up to something similar, because to me the relational way of thinking about so without giving reality to other branches, without assuming hidden variables, works better for quantum gravity. But as usual in these cases, I wouldn't be surprised if somebody who likes a different perspective of quantum gravity, look, I could do the same in my own way of thinking quantum gravity, which is what typically happens about the interpretation of quantum mechanics. And finally, you said, where are probabilities? Well, what the theory gives you is, given some value of observable realized in interaction with the other system, the theory gives you what is the probability of something else happening sort of later on, or vice versa. Given something before, the probability something did happen earlier on. How to think about probability? This, I leave to you, philosophers.
Okay. Just to be sure I didn't forget anyone, could you raise your hand again? To be sure. Didn't miss anyone. Okay, so Karim, you're next.
Thanks, Carlo. It's very clear. Can I ask you a really basic question? Okay. So just could you say a bit more about the recovery of the Einstein equations from the Hamilton principal functional? So I've been trying to understand the derivation myself, and it'd be nice to know a little bit more about how you envisage the connection. There's this work by Gerlach in the 60s. Are you thinking about that derivation, or is there a particular way that you had in mind?
How to get the Einstein equation from the quantum gravity?
No, from the principal, just purely classical, from the principal, the what's called Perez equation, the Hamilton-Jacobi equation.
From the Hamilton-Jacobi equation?
Yeah, for gravity. So from the principal, you said that you can.
Yes. Oh, yes,
all
yes,
the
yes, yes, yes.
information
Oh, sorry.
is contained in the principal
Yes,
function.
yes, yes.
So it was a basic question.
Yes, it can be done. Essentially you have this quantity here. Where now the way to do it, it's in this logic here. Okay. The clean way to do it is you go to time gauge. So your variables is a three-dimensional metric here and a three-dimensional metric here. This is the world of Peretz, not Alejandro Peretz. Peretz, the Israeli guy. Asher Peretz.
Yeah.
Take away T prime and imagine that this is a three-dimensional metric of a region. So you can define a functional now of two three-dimensional metrics, which is defined in the same way. And you basically you take the functional derivative with respect to that, and formally, hiding a lot of shit under the table, you argue that this gives the solution of the Einstein equation, the general solution of the Einstein equation. This is the world from which the Will DeWitt equation was written. So the Will DeWitt equation was written. The idea of young Bryce DeWitt was, hey John, let's do the same that Schrödinger did. So I wrote a few papers of the classical way of doing that. So doing Hamilton-Jacobi for fields in a most invariant way in a theory without time, and it works.
Maybe I can get the references for you later. Thanks.
Right, Sam?
Yeah, just a small point of clarification about the sort of Heisenberg cut in the case of the quantum loop. So, because you said it always has to be in relation to something, does that mean that the sort of the space-time volume or surface that emerges is always some smaller part of a larger loop quantum structure that you then have that relational coupling, or can you do it for the whole thing?
No, you cannot do for the whole thing in the sense of the whole space-time, but you could do it for the whole space, which is what we typically do in quantum cosmology. So suppose it's true there is a bounce, which is what loop quantum cosmology seems strongly to indicate. Okay? So how do you compute the physics of the bounce from this perspective? You cut the the classical sort of effective space-time is like, this, let's say, a compact universe that becomes small and then bounces back. And its dynamics will describe a classical GR sometime after the bounce and sometime before the bounce, but not in between. So now you cut this way, and you want to do the quantum gravity in between. So intuitively what you're doing is a functional integral of all the metrics that start here and start there, okay? Concretely, what you do is use its additional amplitudes, but for a piece of space-time, but now it's all of space. Are you talking about that? No, okay. So you use, this has been done in the technical literature. You try to compute the transition amplitude going from this collapsing universe to expanding universe. And again, the calculation can be done order by order in truncation. And then the technicalities is the truncation reliable, and so on and so forth.
Thanks.
Right. Sumati?
Yeah, so I had, I think, similar question yours, which is to do with, whether there's in this way of thinking about it, whether there's an observer-independent ontology, and in this particular example of the quantum cosmology, so that's one part of the question, but then the second part is more of a question of when you're calculating these, these transition amplitudes, have you thought about, so this is a technical comment, that have you thought about using the kind of double path integral for this, for the decoherence functional? I mean, in principle, the quantum system or the ontology is different for causal sets, but then this is a kind of path integral picture where you can use ideas of the quantum measure, for example, and try to calculate things from that perspective. So I was wondering if, if that particular, whether this framework that you have is amenable to that kind of different approach to thinking about,
yes, I know that. I know that formals you're referring to, because essentially Jim Hartle was very keen on that, using that in quantum gravity a lot. So. I think that it's coherent, it's consistent, it makes sense. I mean, it's coherent, it's called coherent, it's consistent, whatever you use. Yeah, exactly. Exactly. So, but it makes sense, it's a conceptually well defined. You have to, to get the coherent, to get the two histories that they cohere, they have to be in a sense macroscopic. That would allow us to do more than just from the beginning.
The coherence. So unfortunately, it's actually coherence functional.
Yeah.
Because we're not. So decoherence is, of course, in the macroscopic limit, but then we use this. It's a double path integral. Maybe that's a better way of expressing it, saying that that's the right object to look at, and this is how you define the quantum measure. So things that are not decoherent but are well interfering.
Yeah.
Well interfered, cohered parts.
Yeah.
In that framework, which would give you a way of, without having anything external, would, for example, give you ways in which you can calculate sets of measure zero and so on and so forth. So that formalism doesn't seem to be, at least from what I can tell, antithetical. It seems to be something that you could use within.
Yeah. So it has not been done. I don't think anybody has been using the this silver space and the quantum gravity, the quantum gravity operators for doing that. I think it would be possible in principle. I think it would be interesting. The reason that formalism lost, 20 years ago there was more interest in it, or 30 years ago, more interest in that formalism. I think it's related to a number of criticism. Kent, who was Oh, you also. Oh, sorry. Shame on me, shame on me.
Faye will be next for the question.
Which I'm not, now I'm going to explain what the criticisms are because I'm going to misrepresent them.
That criticism has to do with the decoherent history's interpretation, and that's not what I'm referring to.
No, I understand. So, in terms of the fundamental ontology, taking it as a fundamental ontology, to adopt that, I think, requires a discussion about those kind of issues. So, the dependence of the family and that kind of things.
All right, Faye?
Thanks, Carlo, for a great talk. My question is about the truncation and the limit. I totally understand that it's work in progress, that it's part of the, the struggle to define the theory. But I just want to ask a couple of questions to indicate your thinking about it, or vision, or expectations about it. So when you talk about the truncation, is it a truncation on the number of simplices or building blocks in the spin foams that you're summing over? Is it a truncation on the physical space-time volume of the let's call them interpolating or cobordisms or whatever, the interpolating spin foams? And if so, what is the truncate? What parameter are you truncating? And if so, what's the status of the limit? So, in the sense that if you want to really take the limit of, say, the number of vertices or simplices in the spin foam to infinity, for example, that's one thing you can do. But do you really think that you have to define the theory in the limit, or can you stop at some finite stage of that truncation and declare that your theory is that's the theory?
Yeah, very good, very good, very good.
Yeah,
no, very good, very good. The question is very good, very good. So let me answer sort of reversed. First, what I would like the truncation to do, and then how it's defined, instead of first telling you how it's defined. So I start from an observation. The observation is that if I think about quantum field theory, not gravity, the ones we know, and how we use them concretely, we have two quantum field theories that work well. One is QED, one is QCD. They give spectacular numbers. We're very happy with them. We're not very happy with them because mathematically there are problems, both of them. They think we don't understand. But in terms of using them, it's great. And if we were on the same level, at the same stage in quantum gravity, I would be very happy, even if they're all sort of open mathematical problems. Now, the way QCD works, not in the symptotic freedom region, not in the scattering, but for instance, when they compute the masses of the hadrons, is that they put everything on a lattice with a finite number of points, and they argue that the actual physical processes that are relevant are captured at that scale, and what happened at whatever larger scale doesn't matter on the mass of the proton. What happened a smaller scale, a smaller length scale, only renormalize the constant. It doesn't affect the actual process itself. That's how QCD works. And QED most work in scattering, and what you do is compute a certain number of Feynman graphs, which means that out of Fock space, you're cutting away the portion of Fock space up to a certain number of particles, up to n particle number to maximum, which is the maximum number of virtual particles in Feynman graph, and that works. So in both cases, everything we do with the actual quantum field theory is actually calculations in a small piece of the Hilbert space, which correspond to a finite number of degrees of freedom. So the idea is that the idea on which this is built is, can we do the same in gravity? Can we argue that we can do calculation out of the infinite number of degrees of freedom of gravity by picking up the relevant ones, so to say, like the people in QCD say? Okay, so that's the philosophy. Now, concretely, is the first part of your question, how you cut. What sort of truncation is that? It's not a truncation in length or in energy or in anything like that. It's a truncation of the kind that Regge had in mind when he did Regge calculus. So instead of describing the space of all possible geometries, continuous, let's describe the space of all possible geometries which are locally flat, so say triangles in 2 dimensions attached, and where there are 25 triangles. Now these triangles may be small, large, some small, some large. Consider all of them, but I only consider there just 25 flat triangles. And then I do 55, 150. And so in this, the classical configuration space of generativity or space of history of generativity, I just pick some and I restrict them. And then the question is that, is this a good enough truncation? Well, let's hope it is for describing some phenomena, and let's hope that, like it happened in QCD, if I do a calculation with a certain truncation, then I refine my truncation. Let's hope it converges. The quantities I compute don't change too much. So that's the logic. There's a lot of I hope in this argument, but that's the logic. Concretely, we have no theorem of convergence whatsoever. There have been a couple of calculations in which there's one by a collaborator, Francesca, in which in quantum cosmology you nicely see that you increase the truncation and nothing dramatic happens. In fact, things are stable. And my intuition is that, again, the logic here is not describe all the way the fundamental reality or whatever. The logic is that some degrees of freedom coming in I don't know, a black hole is bouncing in a white hole. That's what we're studying. This is a phenomenon at a certain scale. So what we need is to describe the degrees of freedom of that scale, and the theory should pick up what is relevant. So that's the philosophy.
Thank you. Can I just, so just yes or no, I mean, QCD is generally thought of as an effective field theory, let's say, let's call it. So, as you say, it pertains to, you fix a scale and then it's a perfectly good theory for, for that scale. So is that, would you say that
No, I think it's
of loop quantum gravity is
no. I think it's the same we do. It's the same as we do when we really use QED and we really use QCD. We truncate the theory. We throw away. In principle, that thing here are described for every C, for every truncation. So take C arbitrary large. So mathematically, I can define a limit for the. This is a 2 complex. For the 2 complex become arbitrarily large, so you include all the. But that limit, I don't know how to treat it because think about the graph. I could take the complete graph with n nodes and all possible links, and then go n equal 2, equal 3, equal 4, 5, and ask what happened with n going to infinity. But I think that only of interest for mathematicians and philosophers. For physicists, what is interesting is what happened finite n.
So the idea is that limit exists. That limit should exist.
Yes. Sorry.
If it doesn't exist, then that's a problem.
That's right.
The limit should exist.
Yes.
So you could say my theory is really defined in that limit, but in order to calculate some physical quantity, I don't need to. It's enough for me to truncate at some finite stage. But because I know that the limit exists and therefore it's going to be close to the true physical limiting.
Yes.
Okay, so thank you.
Yes.
That's clear.
But I have a finger on this because the existence of the limit has to do with the mathematical definition of the theory, but it doesn't have to do with the idea that you can really have an infinite graph. So there should be a limit. So if you think that the universe is finite and there is a finite and there is a minima size, a finite number of objects inside the universe, so the limit to infinity doesn't really exist. It's more of a sign point. Of course, for the mathematical consistency of the theory, you want the limit to be well defined and so on. But then the existence, I would be careful about talking about.
All right. Next question, Barry. Sorry, we have a lot of questions.
Thanks, Carlo. It was really enlightening. Makes sense of some other conversations we had, which I didn't understand. When I first encountered relational quantum mechanics, I thought, oh, that's just instrumentalism. I see that's not right.
It's not right.
What you're really asking for is a really radical reorientation. This is my understanding now. Just tell me if I'm wrong, of the way physics has been thought of previously. Previously, we're asking for what's the God's eye view of the world. You're now saying, forget about that. All we can do, let me do it this way. If you sort of start, and I think this might be an analogy you use if I remember right, in relativity theory, well, we learn that length and duration are not absolute, they're relative. But there still is something that's absolute. Okay, we do have the space-time interval, it's absolute. I think you're saying nothing is absolute. Is that correct?
Yeah, I think. I mean, this is vague, but in the sense you're intending it, I believe that's yeah.
So that's very interesting kind of reorientation, and it does lead me to. So I mean, one of the things I noticed about it is if you look. I mean, so I'm coming to this from philosophy of physics. I haven't really been thinking about quantum mechanics so much recently. But if you look at the usual discussions in philosophy literature, you don't really find, like in the Stanford Encyclopedia, there's no discussion of relational quantum mechanics, I believe.
Yeah, there is.
There is?
There is an entry which is relational quantum mechanics.
Oh, there might be an entry. And I just looked at the one of the article that says interpretation.
Oh, it doesn't. Who wrote it? I haven't got it.
Fully on him. It wasn't me, but I didn't look at that. But I did just look at the entry, and there's no reference of it. So definitely, it's something that's a new guy on the block with respect to the philosophical literature, and I see that the main thrust of your talk is, and this came up in one of the questions, and it passed very clearly. I didn't quite get your response, but is your idea that, look, if we think of quantum mechanics this way, a lot of the issues about making sense of quantum theory of gravity will just fall into place. We'll be able to make sense of things a lot better. That I took to be the thrust of your talk. That was very interesting, but you also seem to suggest that it's not essential. Is that right?
Yeah, that's exactly right. My sort of popular book of quantum mechanics, which is Helgoland,
I just ordered it.
Has a chapter, trying to look for a philosophical. I mean, there is a lot of relationality in Western philosophy, of course. I mean, with a list of things, but that's sort of more radical. So I went all the way to Nagarjuna Buddhism.
Yeah, I mean, this is a big reorientation of Western thinking about what the goal of science is supposed to be. There is still a flavor of instrumentalism.
Wait, let me go to the beginning of your question. I would strongly deny that there's anything to do with instrumentalism. I mean, if you're an instrumentalist, you're at home, but that's not the point. I don't want an instrumentalist at all. And the main point is that in relation to quantum mechanics, if there is a system and the other system with respect to which variables are defined, this other system doesn't have to have any property. So it's not an instrument, it's not a human, it's not a consciousness, it's just a piece of wood. So I think there is a common confusion between relative and subjective, which is silly, okay?
Sure.
And it's a confusion which is fueled by physicists' talk when they say in Galilean relativity, velocity is defined with respect to an observer. That's not instrumentalism. That's just a property of velocity. the moon has a velocity with respect to the sun, but it's not that the sun is an observer in the loaded sense of the. So velocity is a relative thing. So what I'm saying here is that variables are relative, and what comes after that.
I was shocked when I found out who wrote the article in the San Francisco Encyclopedia. It's by Janan.
Yes.
She should not have been the person to, she should have taken.
I'm going to insult her.
Okay, last thing in my mind, it came up also, is I was trying to get my mind about how you think about probability in this account. The dynamics from within a perspective, it will be probabilistic. But the natural question one wants to know is what facts about whatever, the perspective or something makes those the right probabilities. You might want to say that they're just primitive, I guess, but.
Look, I've been reading about interpretation of probability. The last time I read is Wayne Merrill's book on chance.
Say it louder.
I've been reading about the general philosophical problem of interpretation of probability,
Right.
and every time I read a new thing, I change my mind about what is right interpretation of probability. So
I have a big long discussion in the book I just wrote. Actually.
okay, yeah, I'm going to change my mind once more. As a physicist, I take probability of vaguely defined concepts, which can be defined different ways that typically that doesn't work. But here, as a physicist, remember, I'm describing phenomena, and in the same world, phenomena are repeated. And so, since as a physicist, I came up by doing experiments many times. For me, those probabilities are just something I read out of the world from frequentism and induction. I mean, if it happened 10 times, I think it's going to happen next time. So I read them out of frequencies, and then because of that, they become subjective, is what I expect to happen again, because of induction, which I know can go wrong, but still, I use it. So I'm very hand-on. Why there is this repetition in the universe? Because I'm also asking that kind of question. Probability is a tool for describing regularities that I see in the single worlds, which I repeat many times experimentally. And this is at home in what you were describing.
All right, let's move to the next question. I will put me in the queue. I want to follow up on some of the points by Emilia. Ask you about the process. How do you think of processes? Because in philosophy we have a catalog of different things that could correspond to how you think of the processes being involved. So I was wondering, perhaps, could you say how you think of the relation between processes and causation? Of course, we also have a big catalog of different sorts of causation, but are you interested to have a more fine-grained discussion of what's the metaphysics of process? Or do you want to just stop there and you're not really interested by that? If you're interested by this question, what are the options on the table by your left?
Okay, there is I can answer in two parts. There is a part which is I can just repeat things which are in the literature and be a spectator of a discussion, and there is a part which is I think not common in the literature. So let me separate one. The first part, I noticed that in physics we talk less and less in terms of objects, and then I'm as a physicist, I mean, how do you know if somebody is a relative? You ask, what is the shape of the sun? If it will answer, well, it's a sphere, more or less, it's not a relative. If you answer, well, of course, it's a cylinder, more or less, right? Then it's a relativist, okay? Because the sun is a cylinder. It's the history of the sun. So the sun is a process. It's not a thing. And in fact, the sun is a process in many senses. It's burning. So an object, like Goodman says, is a monotonous process from the perspective of the physicist. So the notion of object goes away, and what you describe is things which live classically in a four-dimensional region, not in a three-dimensional region. Things happening. That's a discussion which is in the literature, the philosophy. It opens the kind of question you were asking. I have nothing more to contribute than the various views in that. What I think there is an aspect of novelty, of radicality, is that I think one can think in terms of processes, things which describe four-dimensionally, not three-dimensionally, without being forced in any of the intuition of the block universe, without assuming a preferred direction of time. So you can talk about happenings, plural, and processes, without having to say, oh, I have to think that this comes first and then this is happening in time. The fundamental physics that I know, forget quantum gravity, from classical GR and from the standard model, is not a time-oriented physics, but it's a physics of happenings. And that's, to some people, it's hard to digest. That you can, for some people, taking away a direction of time immediately puts you into a block universe. And I think the wrong aspect of the intuition of block universe, the block universe is static, nothing happens. But it's not nothing happens, we're describing happenings. They're describing what we call happenings.
Right, okay, good. I mean, just some people in the block universe tradition defend that the space-time relations are themselves dynamic, so it's dynamic building blocks. That's one step in your direction, because then you want also to destructure things and have local happenings. But you have some friends there as well.
The block universe is a la U Price. When U Price says, what are you saying about the world which is not saying in my block universe? I agree. It's just numbers. As if you take too seriously the metaphor of block, stone, then you get wrong.
Fair enough. Thanks a lot. All right, let's thank Carlo and Emilia.